All right, hello, thanks everyone for coming. My name is Gustavo Moura. I'm a software engineer at Snap.
My name is Ben Dodson. I'm also a software engineer at Snap.
And you may or may not have heard that over the past year or so, Snap has been rewriting its Android app from scratch. Today we're going to talk to you about that. We're going to talk about what the problem was that prompted us to do this, what kind of solution we came up with. We're going to go into a little bit of detail about the platform that we've built to overcome a lot of the hurdles that we ended up facing when we tried to do the rewrite. Then we're going to take a step back and talk about why do we think the rewrite was a good idea and how we're actually launching it now that it's almost ready. So I'm going to start by talking about the problem, and this is the problem. If you don't know what this is, it's systrace. It's one of the most powerful tools an Android developer has for profiling your app and understanding its performance. You don't need to try to read anything here. The summary of the slide is there's a lot of stuff going on. This is a profile of the main thread at the startup of Snapchat. Up the top there, if you could read, you would see that it takes 2 seconds. And that's not super bad for an Android app, but for an app that wants to be your camera and wants you to use it when you're about to take a photo of a fleeting moment, it is not good enough. The reason it takes 2 seconds is that there's a lot of little things going on here from a lot of different places across our app, and in aggregate, it just causes problems. So going a little deep into the problem after a lot of profiling, the real reason why Snapchat was slow to start up is that Snapchat is really a lot of small apps rolled into one. Snapchat is a camera app, it's a chat app, it's a video app, maps. It allows you to edit the photos you take. It has augmented reality, and so on. There's a lot of functionality in it. It's good to have all of this in an app. You can do a very powerful experience for your users. Almost any app you see out there could be divided up into multiple ones, but we don't, because it makes sense to take users smoothly from one place to another, but it does cause a lot of engineering challenges when you try to get everyone to play nicely together with everyone else. Usually, the way you organize a bunch of apps is you have an operating system that says, OK, you can get the CPU and you can run. The user's not using your app, so shut yourself down and so forth. When you bring it all together, you have to kind of do the job of the operating system yourselves. The reason we ran into so many problems and our app was slow is that the way we built Snapchat was essentially by using the best practices of Android development at the time we started, which was 6 years ago. At that time, everyone was using a global event bus to communicate between features. Everyone was using a view pager to load all the different sections of their UI. And as you know, a view pager loads every single fragment instantly on the main thread, right, as the app's starting up, which is not good. We had a bunch of get instance calls because Android up to very recently was synonymous with static state all over the place. And we had a sync test, which is this amazing utility for controlling your background execution, which doesn't work well at all. And finally, JSON to wrap everything up. This is not specific to Snap. I think everyone, if you look back 3 years ago, or at least if you look back 5 years ago, was doing this, right? This is just how we did Android. I think what was specific to Snap was how quickly we grew from being an app with a few thousand users to hundreds of millions, how many features we had to put in the app to support those users, and how fast we did all of this without really taking the time to take a step back and rethink our architecture. So we took scaling pains. When things were bad enough that we decided that this was absolutely something that we had to do something about, we took a really hard look at how our app was structured. And I think the best idea we had was to think of this app that's a bunch of different apps crammed into one as different apps crammed into one. So what we thought about is, well, we have all these different apps. We're not going to start shipping a bunch of apps in the Play Store, but what if we actually develop them as separate, smaller apps, right? And when you start thinking in those terms, it becomes a very powerful idea because we had problems, for instance, where a feature of our app, like your friends list, was slow to load. So the team decided that it was important to load that feature at startup so that when the user swiped there, it was ready. But when you think of simpler, smaller apps, you think, well, there's hundreds of apps in the Play Store which have a friend list. Most of those apps load pretty fast on its own. So why is it that our friend list cannot load fast on its own? And the answer to that question was, well, when you're trying to load the friends list, that's all this other stuff running as well, right? So our idea was, let's have all these small apps. They all have to be fast by themselves. And if they're all fast by themselves, then when you put them together, you don't have to preload anything, because when the user swipes to a page, that page can load quickly. And then you remove all the things that slow you down, right? So we came up with a very simple contract. We divided our app into modules. Modules are not allowed to do any preloading at startup or not do any work for the most part when they're not running. Each module had a standalone sample app to come with it that was basically a way for you to develop your app and prove that it's fast in isolation. And then if your standalone app loaded fast, the promise of our platform was that when you put it all together, it would still be fast. And working on the platform team, our job was to ensure that that contract was held. So we put this to practice. We divided up our app in all these smaller modules. This is a sample of our module for a memories feature. It has an API submodule, and all of these are Gradle modules. It has an API submodule. That's how everyone else interacts with it. It has a core module where most of the implementation lives, and then it has a sample submodule, which is where its sample app lives. So every team in the company built one of those. We could open the sample app and see, oh yeah, the sample app is fast. Okay, hook it in. Or if the sample app was not fast, we would be able to know that, okay, your code is not yet ready to hook into our new rewritten app yet. Make it fast first, and then you can plug it in later. This is kind of an overview of our layer of our app. In the bottom, you have a platform. This is standard stuff like storage, networking, image loading, and so forth. In the middle, you have all your different feature modules, right? So things like your friends list, your chat page, your camera, the edit tools for your camera. Each of those are a pink box. On the top, you have all of your different apps. And some simple apps can be very simple and just depend on one feature, but others may need multiple features to run. For instance, you cannot really have a simple app that tests your augmented reality without also having a camera. But basically, you have all these simple apps that pick from these features, and then you have your Snapchat app at the end that uses everything. So our camera sample is the simplest app we have. It only uses the camera module. We ended up with 16 sample apps. You can see a screenshot of some of them here. Our map sample app is only like a very simple menu that allows you to log in, log out, and a button you click that loads the app, and then you get to see the app functionality. The one on the right is also very simple. It's just for augmented reality lenses. It's just the carousel, so that you can tell that the carousel loads fast. Then we have another sample app that puts that carousel on top of the camera so that you can actually interact with it. And we ended up with 2 top-level applications, old Snapchat and new Snapchat. Old Snapchat didn't use most of these modules because if we were able to entangle everything, we wouldn't have done a rewrite on the first place, but it did use some. And then the new Snapchat was completely using the pattern that I showed you before. So that's the idea. We thought it was very powerful. We decided to push more towards it. But when we put it all together, we ran into some problems, and we overcame them. And Ben's going to talk about what some of those were.
Yeah, so a bunch of modules sounds simple, right? And they'll just magically work together. Turned out to be a little bit trickier than that. So let's step back and focus on one particular problem inside of Snapchat. So that's the particular swipe. So you bring up the app, go into your camera, and swipe from left to right to get into your friends feed. And so as we said, we want the camera to load as quickly as possible so that you can grab the picture that's right in front of you. That's kind of the most important thing. But it also needs to be very fast to communicate with your friends. So you'll see on this GIF, there's a little bit of kind of jank right there at the end. That is unfortunately not an artifact of the GIF. That's actually part of the app. We'll talk a little bit about what caused that and what we can do to fight it. So again, we're thinking about rewriting the app. This is a good chance for us to kind of reset and adopt a lot of modern practices from the last couple of years. So we spent a good amount of time researching what was out there, what was kind of industry standard today instead of industry standard circa 2011, 2012. So we studied RxJava, Dagger2, a bunch of options for the persistence layer, ended up with SQLite and SQLite, and of course heavy use of Kotlin, which has been a real joy, and as well as a bunch of other smaller libraries that really help us get a lot of our work done. But even with the abundance of excellent software out in the open source community, there were still a number of problems that are some specific to Snapchat, some not, that we felt like we needed to build our own libraries to support. I think in particular, most notably is a navigation framework I think is very unique to Snapchat. We have a very swipe-heavy experience. So even though we got started before the navigation framework was announced at this year's Google I/O, I still think we would have had to do our own just because of the extreme nuances that we have in our user experience. So in addition to that, we have a framework for managing UI, mainly for recycler views, to load them as efficiently as possible. And also, we're a very multimedia-heavy app, so we have a couple of frameworks for managing multimedia, both loading, fetching, as well as processing for when you have a snap and you're applying your edits on top. So I wanted to dive into a couple examples. This is real code, but it's kind of pseudo code, but I think it compiles. So this is diving into our navigation framework, which we call DEC. So there's a part of our code that's very much like a builder, which kind of outlines the way that our application is composed together. So we talk about having the different modules. This is where they're actually stitched together. So diving in, specifically, let's look at how the camera gets created. So we have basically an enum that represents the page. Obviously, an enum doesn't take that much time to load. But you'll notice the camera fragment, which is what actually backs the page, we pass that in as a lambda. This is actually what gives us kind of the flexibility to load our features on demand. So none of our content is loaded until it's actually needed by the user. So in this little piece of code, we're both creating the camera fragment and also specifying the page to the left and page to the right. So if you do a left to right swipe, you'll end up at the friends feed. And if you do a right to left swipe, you'll end up on the discover feed. And similarly, if you're on the friends feed and you do a right to left swipe, you'll come back to the camera. So this is where our navigation framework kind of shines, is in these transitions. We have a couple of kind of more exotic ones like pinch to get to the map, or a couple of different ways to do swipes. So sometimes we slide the content in, sometimes we fade it or blur it. And so that all kind of gets baked in here at the navigation stack, and you don't have to kind of muddle your code up to get that done. Another thing to point out is this is like our camera main. So this is like our front page camera. But we actually have other cameras that, for example, don't swipe from left to right. And so that's just a matter of loading up your fragment without these navigation actions. And again, we keep that code way out of the way of the camera, so it doesn't have to be concerned with any of this navigation logic. So that's how we compose our screens together. But again, we really want to make sure that the Friends feed and Discover feed and all these other screens can load as quickly as possible, especially given that we're loading them on a swipe. So anything that's on the main thread is going to be very, very noticeable as your swipe just gets jankier and jankier. So we really adopted this pattern of unidirectional data flow. It's both kind of the observable community and React Native kind of, I guess, popularized this pattern in UI. But really, this gives us kind of two benefits. One is like making sure the state is kind of consistent. When you're applying state at the view level and then something changes further downstream, it's pretty easy to get that out of sync. So it makes it much easier to write less buggy code. But also the performance is much easier to reason about when you have this kind of staged pipeline of going from data to view model and finally to view. It really gives you an opportunity to tune the work and get as much of it off the main thread as possible. So this is what it looks like in a bit of a diagram. So at the top we have our main thread. Of course, there's only one. And our goal is to do as little work there as possible, which means we move everything else to the background thread. So pretty much all of our screens, Friends feed, Discover feed, Send to, have very similar patterns where there's some data source, load some data out of it, do some processing, convert it into something that's going to be more appropriate for the screen. Maybe it's formatting timestamps, formatting names, localizing things. And only once that work is done do we then present it to the views to put on screen. So once we built this, the first thing we realized actually is view creation is actually really expensive. It's basically, if you run a systrace, you'll see that about half of our jank was actually just coming from inflation of views itself. So certainly we can do more to improve our views, flatten our layouts, use fewer views. But at the end of the day, even if you use the minimal thing of just like a frame layout and a text view, it still takes quite a bit of time. But fortunately, about I think 2 years ago, Google kind of officially relented, the Android team officially relented and said, actually it's okay to create your views on a background thread. They introduced something called the async layout inflator, which is the first time when they said, actually a view can be created on a background as long as it doesn't require a handler, right? So this can happen, for example, if you have a gesture detector, then the only change you really have to make is make sure that that part gets loaded on the main thread. But once you move your views to the background, roughly cuts the work that we have to run on the main thread in half. But it also lets us create those views in parallel, right? Because they're totally independent. We're basically just doing the same thing over and over. So that lets us both decrease the amount of jank, which is what's on the main thread, but also the total amount of latency since we can parallelize some of this work. So we take this pattern and we embed it in a framework so that it's easier for our teams to adopt. The framework is called Recycling Center, which helps us manage our recycler views. So this is kind of what the top level code looks like to build this screen. This is our snap sending screen. So there are kind of two main features of this platform. The first, as we mentioned, it's reactive. So we have this unidirectional data flow model. But the section it's very sectional, right? So our UIs just kind of in the last couple of years have evolved to be very kind of section oriented. So you see this one, we have a story section, best friends, and a recents. All are obviously very different data sources, different UI, different interactions. So it really makes sense to kind of group their code, separately. This also lets us, run different A/B tests, where we can turn off a section, turn it back on, without having a total spaghetti mess all over our app. So let's take a quick peek. So we see, for example, the recent section we created. That's where our view models get created with an observable pipeline. And we're passing in a query, friendsrepository.getRecents. So that, if you go to the next slide, for that we mostly rely on SQLDelite and SQLBrite here, which are the SQL libraries put out by Square. So, we had a very tough choice between Room and SQLDelite. We looked at a lot of options, but those were the two that really were most appealing to us. Frankly, it kind of was a toss-up. I think Room at the time was in beta, so that was, a little bit of a sell in the direction of SQLDelite. But the thing that I most appreciated about SQLDelite actually was the way that you specify your SQL statements, which is just as kind of a pure .sq file with nothing but SQL. This to me felt like it had the chance of being multi-platform, which I know is kind of a distant dream, but like it felt like if anything could do it, this had a chance. Maybe we could write our own Objective-C generator. Well, it turns out in the most recent release, if you guys aren't SQLDelite fans, they actually have now added support for Kotlin native, so this turned out to be hopefully a good bet. Maybe that's something we can take advantage of in the future. But so at the end of the day, we just write our SQL query as just pure SQL. The other nice thing about SQLDelite is it has you can specify your queries, and they will generate a data model that has just these fields in it. So if you want really efficient SQL statements, it's good to select as little data as possible. And so rather than doing a select star, this really helps you write select in a listing of the fields without breaking your app, right? If something gets added or removed, instead of just having a null pointer exception in your code, you'll actually have a compile error, which you'll know to have to resolve. Okay, so that takes care of loading kind of the general UI, but we're obviously a very multimedia heavy app. In our old app, I personally struggled quite a lot with how we were managing basically thumbnail content. There are a lot of very complex rules about how a blob might get downloaded from the internet, different sources, whether it's S3 or wherever else. But also we have various encryption policies on different media types, just totally different storage rules. And in a lot of cases, that code kind of ended up right at our UI layer and really kind of made a mess of things, not to mention slowing things down quite a bit in ways that were very hard to debug. So for this, we kind of turned to the content provider model. So most people probably know content provider as kind of an abstraction over a database. It has insert, query, update, delete methods that map basically directly to a SQLite database. But there's a slightly lesser known API that's about opening an input stream for a kind of a file path, which turns out to be a really nice way to abstract your front-end code from the code that might be used to load that content. So here we see this is a view binding for our Recycling Center framework. You see the first line we say is thumbnail.setImage URI, and all we have to do is pass in the URI and not worry about how it gets generated. The URI is not like an HTTP URI, but it's actually a local like content : / URI. And so there's some other piece of code that helps us understand what that local representation means and how to download it. So jumping to that. So this is the URI handler. And so we rely on Dagger here to help us keep this nice and modular. So it turns out we have about like 50 different kinds of content that we can load. Each one is just implemented as its own URI handler and done in its own independent module. So we have like emoji, story thumbnails, et cetera. This is where you might look up the database to get the field. This is where you'll do your caching, your decryption. Some of our content comes in a zip file, so you can download the zip, cache it, and return a single asset out of there as well. All of that can be hidden away from the UI inside of this URI handler pattern. So again, this is something like the framework here that we built is actually really quite small. It's more of just a pattern that we use to help us keep the code nice and tidy.
Fastback.
What's that? Oh, right. Yes, diving into the code, of course. Okay, so there's basically two main parts to a URI handler. So the first is you specify a path spec. So this gives you a path. This would be like /story thumbnail / blah blah, whatever arguments are actually used to load that content. And the second part is how to actually resolve that content. So the first part is used to basically inject you into a map, using Dagger injection. And the second part is actually how you run your code. And so basically that's all there is to that framework.
All right, so Ben described in a little bit of detail how we go from our data layer all the way to the UI layer for each page. The problem that we then ran into is, okay, you have this app, it's very well modularized, you have all these standalone features, but when you put it all together, you end up with all these kitchen sink pages or kitchen sink modules, which are places that either depend on everything or that everything depend on. One good example of that is the settings page, right? Like every feature wants an item on settings. So the settings module ends up depending on every other module. To break away from that, we use Dagger, and we use Dagger a lot. So basically, for the settings page, you have an interface for a settings item. That implementing that interface, you describe what the name of the item is, which section of settings it ends up on, and then you add a click listener to be handled when the user clicks on the item. You inject it using Dagger via multi-binding so that any module from anywhere in the application can inject into settings. And then settings doesn't have to know about logging in and logging out. It doesn't have to know about anything else. It's just a simple page with a list of items. We use this not only for global pages, but also for local feature pages that were getting quite complicated. One example of that is our editing page for snaps. You have a lot of things that you can do to a snap. You can change the color. You can add stickers to it. You can add text. In this example, you can set a timer so that it disappears after a while. And the way we handle that is by, once again, defining an interface for what an edit tool might be that had essentially an icon, some definition of which types of media it applied to. Some are only for video, some are only for images. And finally, some behavior that it performed when the user clicked on it. Once again, we implemented that tool. We bounded using Dagger, in this case, map binding, because there's a key that's important elsewhere in the edition flow. But that allows us to decouple all these small features from the main page, which is the one that allows you to view the photo you just took and has to load super fast and be very reliable and work really well. Next example is of our network request. This is what it was before. I apologize. Most of our slides are probably not very readable from the back, but this one's meant to not even be readable from the front, because this is how much code we used to write before. If you could read this, you'd see a lot of different things here. This code is for a class called sync friends task, which would sync friends with the server. It has code for encoding the payload, decoding the response, creating the request, and also doing the business logic for handling the response, all in one place, all together, very hard to follow, very easy to break. Afterwards, we're able to use two things to make this code much saner. One was retrofit, and the other was RxJava. So first I'm going to talk about retrofit. On the top, you can see our HTTP interface for this request. Retrofit allows you to very concisely define what the request is, right? So here you can see the response, the request type, and the endpoint that you hit. And it's all here. All the parsing, the encoding, decoding happens in framework code. With retrofit, you can hook in many different encoders and decoders for different types of payloads, different types of responses. You can also add more annotations if you need, for instance, for a request to be authenticated or to do different interesting things that you might need to do when talking to your endpoint. But we define it in one place, and then here's where we use it. So this code has 3 steps: creating the request, sending the request, and handling the response. Creating the request is pretty simple. We just create an object, do a database call to get a sync token, attach to that object, and then we're done. But we call this RxJava method subscribe on to ask for that code to be run on the I/O scheduler, since it's going to be doing a database call. Next, we do a flat map to take the request, pass it into our nice retrofit interface, and send it. And we do that on the network scheduler. So that takes care of doing the request encoding, the network request, the decoding of the payload, and giving us a decoded response. Finally, we take the response, and we call into our friend repository to apply it, to save the response to the database, and we do that on the database scheduler because it's right into the database. This code is very concise, very easy to follow, very easy to see what's happening and in which, and also to control which thread everything is happening on. The actual implementation of how you handle that response lives elsewhere, which I think is a good thing. You don't want to be combining too many of these concepts together. To close, I'd like to show this slide here from Google I/O. Finally, this year, after 10 years of Android, Google gave some opinions on how you should structure an Android app. And being an Android developer, I'm very happy about that. Basically, at the top you have your UI, and then you have view models or some binding layer that takes your data models and turns them into models for your UI. Then you have a repository which manages data that could either be coming from a database or could be coming from remote data. I think most companies are converging into developing Android apps in that manner today. So it's very nice for Google to officially support it. Unfortunately, I had to scratch some of the names and replace with the libraries that we built ourselves because the Google libraries didn't exist at the time or they weren't quite sufficient for our use case. But I really look forward to the future where every Android developer is speaking the same language, and we can decide, okay, which library is better for doing view bindings for my particular application? Should I use this Google library, or should I use this library that's Square open source, or should I build my own thing? I think that will be a much more constructive conversation than just trying to come up with the whole architecture of the application from the ground up. Now we're going to talk a little bit about why we decided to do this as a rewrite.
So early on in this process, we knew we needed some big changes in the app, but we weren't yet sure if that was going to be a rewrite or just some refactoring in place. It was really a very long and painful conversation to get to make a decision here. The thing is, a rewrite is really a bad idea, like period. You shouldn't do a rewrite unless you really, really have to. Especially when you're at scale, like the biggest problem with the rewrite is you can't actually ship it to your users until it's completely done. So if you're missing one feature that like a small number of users want to use, well, you still can't push it out until that feature is there, or else you're going to really have some very unhappy users. So it's not like adding a little feature which you can put behind an A/B test and turn it on as you wish. You really kind of have to get the whole thing done before you can really get any benefit at all. It's also so we sweated over this decision, but we thought on the other side, like, what are the reasons why we might have to rewrite this app? The thing is, fixing things in place is very, very slow. So we didn't have an effort to modularize. Like, that could certainly be done in place, just pulling things apart, moving them here and there. But as you go, you realize all the small mistakes that crept in because the modularization wasn't there. So you have things like Bitmoji taking a direct dependency maybe on Discover, just for example. Just things that can easily happen when there are no firm boundaries in place. And those tend to be very, very challenging to try and unwind, especially when it was code that was written a couple years ago and you don't really know what the origin of it even was. But really, for me, the biggest factor that told me that rewrite was the way to go, performance is really not something that you can just kind of layer in at the end. Like, performance is not just something that you can change a few lines of code here and there, and you have all of a sudden a performant app. Performance is really about getting the foundation of your app sound and correct, and then building on top of that using best practices from there. But if you don't have a strong foundation, you're going to have a bad time. So we in a lot of ways didn't. One of the most challenging parts of our app from a performance perspective, so we have a SQLite database. What we would do, take that database, read the whole thing into memory, process it, and only then, once we knew what content you needed, we would make our network requests to get your messages. So this actually works very well if you're on either a very fast device or if you have very little data. And we are an ephemeral messaging platform, so it's conceivable that we don't have that much data. But as the app grew over many years, we grew from maybe a handful of tables up to about 90 different database tables, all with more and more data in them, right? So all of a sudden, loading the entire database in startup turns out to be not a very good idea. But the problem with this, it's not that easy to just change that, right? Like, once you build your code relying on everything being in memory, it's very hard to just convert that code to be reactive and to expect the data to be at rest instead. So, how long would it take to just change this one thing across every feature? I'm happy to say that I don't have to know that answer, but that was one big driver for saying this might be the right way to go. So we've been working on this for over a year. Recently, we have started actually launching it.
It's not out to everyone yet, but we are in the process of doing it. When we thought about how we would launch this, I think the main thing that we wanted to do is not have to support 2 apps at the same time for too long, right? It's just too complicated. So we took some approaches that ended up being pretty successful to do that. The first one is we did this in stages. First stage was we just built the platform. We thought about, okay, what we're going to need to be able to modularize this app and make it performant. So we built those pieces first. Only like a few teams and a few people were working on it. Everyone else was continuing to develop the app as normal. When we thought we had the platform ready, we took 2 modules and we modularized those first completely in a vertical way. That allowed us to find bugs on the platform that we've built and also find things that we missed on our original definition of the platform and build that up first so that when we moved on to the rest of the app, we were very confident that we were ready. Only when we had done these 2 stages, we onboarded everyone else and said, okay, come on and develop your feature, help us rewrite the app. At that point, the whole company was developing on 2 apps. We still did not want to have users using 2 apps, so we made sure the app was very usable before we did that. And the first thing we did is we allowed users to opt in. Allowing users to opt in is very good because they have signed up to have some sort of pain when they opt into an alpha version of your app. They can always opt out if a feature that they miss is missing or something is not working correctly. And you don't need as much level of support for that as if you were forcing users in. Only when our app was very, very ready and we had been using it internally for a while and we had been listening to users' feedback, and that feedback was really good, we started forcing users in. The goal was to then minimize the amount of time where you have public users using 2 different versions of your app that you have to support at the same time. One very important thing for us to do along the way is to adopt an MVP mentality. That basically means don't build everything and have a working app at the end, but have stages in the middle where you have a subset of your features that are working really well, right? So we made it a point to have the performance always be good and enforce that with automated performance tests. We made it a point to not have the app crash too much or not crash much at all, even when it was only an internal app. And that allowed us to use the app ourselves and find bugs and keep the quality high as we were building it. And then as new features were getting ready, we enforced the same quality bar so that a feature wouldn't be integrated into the new version of the app until we thought it would keep the quality of the app and the performance of the app high. This involved a big effort. We had 90% of our Android developers working on this at some point, and we still have a good amount of our Android developers working on the migration today. This is a little snippet of our spreadsheet. It's much bigger than this and very scary. But it was a very collaborative effort. It was very important that everyone felt that they were working on one thing and not, as a bunch of different teams trying to do their own part. Here's some demos of how it works. Hopefully we'll play. Yeah. So left is the new app, right is the old one. You can see the camera loads faster. Next one is loading your friends list. So left is the new app. Loads considerably faster. And it's similar in all the different pages of the app. Not only loads faster when you take an example here, which I'm not sure quite which phone this is, which is somewhere in the middle, but as you look at the P90 cases and the P99 cases, the performance difference is even bigger. So we decided to launch this when we thought it was ready. The idea was to enable an opt-in very slowly, only to a subset of countries, a small percentage of users. We wanted to hit 100,000 users and hold there so that we can learn. When we put the code in, before we even turned the opt-in on, what happened was people started decompiling our apps, and they figured out that you could root the phone and switch up some lines on the manifest to disable our old activity, enable our new activity. This caused all sorts of hell. We got too many users way too quickly. Those users were not enabling the app correctly. There were a lot of services that they were forgetting. So the apps were crashing all the time. Our crash rate went through the roof. We couldn't learn anything at all from the opt-in users. So we did 2 things. One is we actually put code in our app that would detect if someone was trying to change the manifest to opt into the app, and we would fix the hack for them so that they would opt in correctly. That reduced our crashes. But then we had a different problem where people started talking about Snapchat Alpha. And if you search Google for how do I enable Snapchat Alpha, the first result will be an article telling you to root your phone. And we didn't want the majority of Snapchat users to have a rooted phone, so what we ended up doing is we put an Easter egg on the app. You can go on Snap Maps, you can search for Bermuda. There's a little ghost there, and if you click on it, it allows you to go in. Now when users search for how do I enable Snapchat app Alpha, they see, oh, open Snap Maps, go on Bermuda and click on the ghost, and they're like, really? But it works, and so we don't have as many people rooting their phones now.
By the way, the island is actually called Alpha Island. So.
Yeah. And so we have a lot of users opted in, and we're hearing their feedback. The feedback is mostly positive. A couple of screenshots. This is from the person who actually found a way to hack into the app. She says, after a day of trying the new Snapchat, I guess I'll start using it more often than I did before, so add me. This is a screenshot from Reddit where someone asked, well, how quickly does it launch compared to the old one? Insanely fast. So the feedback was very good, but we also heard a lot of bad feedback, mostly about bugs that we introduced when we rewrote or missing features that users really wanted. So we learned a lot of lessons along the way. I think the most important one is that rewrites are okay, but make sure it's your only option. We cannot emphasize enough how painful a rewrite can be. Really try to minimize the overlap between both app versions, both for developing both versions, and more importantly, for having both versions out to users. You can learn a lot from your users, both by measuring their engagement, but also from just listening to their feedback. And finally, what we've learned is performance does matter. When we did all this effort to improve the performance of the app, users noticed. Even though the app didn't change at all, they said, wow, the whole app is so much better. I love the new UI. The UI is exactly the same. It just works faster. So it's a worthwhile effort. And that's it. Thank you. Question?
So how did you handle on your side offering the two apps? Was it did you have different packages, or was it that within the same app? Did you make them download both apps and one?
Right. So the question is, how did we manage to have two apps, right? So we really wanted to control the rollout in ways that the Play Store doesn't allow you to, right? The Play Store is very limited on what kind of targeting it allows you to do. So we basically have an app within an app, right? And we have a little library. We have an app within an app. So we ship both apps in the same APK. And basically, all the activities of the old app and services of the old app are enabled by default. When a user switches, we disable all those activities, all those services. We enable all the new ones. We change our launcher to redirect to the new activity, and then we restart the app using Process Phoenix. Once we launch, we hope to talk more about that, but that's the general approach.
And so initially on this, we were very concerned that our app size was just going to go pretty crazy, but it turns out, we're sharing the core libraries, we're sharing our assets, so ultimately our app size didn't go up that much.
Yeah, I think we went up by 2 megabytes on a 60 megabyte app, so it wasn't, yeah. The downside of doing that is essentially just complexity, right? Like you run into all these different corner cases that you didn't expect. Like you just switched all these services and you restarted the app, but then the Android system nicely tried to restart one of those services that you just disabled, and then it caused a crash. So we had, but yeah.
So I have two.
Mm-hmm. So 2 questions. The first one, how long was the overlap? And the second is, how do we know performance is better since we haven't added all the features yet? So I'll answer the first question, then you can answer the second one. So the answer to the first question is we don't know because we're not done yet, right? Like we don't know how much longer it's going to take. But the way it kind of worked is development-wise, we had a bunch of features on the roadmap, and we started trying to align our roadmap with our rewrite roadmap, saying, okay, at this moment, your feature will have finished all of the launches that you want for this year, and then you will start the rewrite, and at that point, we'll be maintaining the old feature, right? So it wasn't, at one date, we stopped the whole company. It was more of an interleaved process where each team had their own timelines. And then, as far as launching, we tried to minimize as much as possible, so only when we thought the app was ready, we started forcing users in, and we think that time will be as small as it possibly can be, but we don't know yet because we're not done. If you ask me this question again in 6 months, I'll be happy to tell you.
And so as for your question about how can we tell that the performance is better given that we don't have all the features? So the most important part of this rebuild is that we don't let features run until they're requested to run. So we know that once we add more features on the preview page, like maybe custom stickers, for example, we know that's not going to have any impact on the friends feed or on the camera. Yes, there might be like a small amount because of like DeX packing and DeX loading, but our performance issues, like that comes up a little tiny bit, but not so much in a production build. Our performance issues are really when like a feature is running its code when you're trying to run your own feature's code. And so that's something that we put like hard rules in place so that we know that that's not going to happen. So as we add the custom stickers back, we know friends feed won't be affected. We have in the back.
Did you get that?
Yeah, so the question is whether, while we were rebuilding the app, whether we could rethink how we're doing accessibility. I think the answer to that is kind of yes. The answer is more like we had some accessibility work on the roadmap that fit much better into a rebuild. So yes, we could certainly account for that much better. We do have a bunch of parallel efforts going on around like making content more available to people who can't, for example, see the content. Also, like left to right and right to left is something that we historically didn't even do that well. So that is something that we paid much more attention to as we were going through all the screens. I wouldn't say that's, we're not 100% there yet, but I do think we're in a much better place to be supporting these kinds of features.
I think one theme that we saw in a bunch of places is that we used to have an app where everywhere in the app you did things differently, right? Now we have an app where there are structured patterns, and almost everywhere you do things the same way. So any cross-cutting effort, like accessibility or supporting right to left or compressing your images, is much easier to roll out because it's very easy to see what you have to modify, and it's the same everywhere. Yes?
How did you get buy-in from the team and the company to rewrite the app?
Maybe we should get some beers.
Yeah, right. Meet us afterwards.
I think in general, there's two things that really helped. One was that we didn't just decide to rewrite the app, right? We decided that we wanted to fix some problems in the app, and we tried to do it the incremental way first. And we suffered with that pain for a while before we saw that it wouldn't work. And then we tried a different way, and we did a prototype essentially where we said, okay, what if we started from scratch and we did these things that we talked about today? We didn't just present these slides to leadership and say, please let us do this. We built a prototype. So 10 of us actually spent a couple months just working on a prototype that would prove that this would work. And then we presented it to leadership. So at the time that we presented, we were pretty certain that the approach would work. What we didn't know is how long it would take or what other problems we might face, right? But we were pretty convinced that we would work and that we thought was absolutely the fastest way to get us where we wanted to be.
So I think these two questions are actually very interesting together of, how do we build a prototype that we know is fast? And given that we know the prototype is certainly not going to have all the features. So that's where we really had to, build the platform as kind of honestly as we could so that we could say with a straight face that as we add complexity to the screen, it's not going to slow down except for the immediate slowdown that you add, right? So we had to make the platform kind of correct enough that when we showed the UI, it was not a fake UI. We felt that we could get all the features in without slowing down that screen.
Yes.
Okay, so the question is about async inflation and whether that was enough to kind of cure us of jank. So I think it was about half of the time initially was dedicated to just inflations on the main thread. I think it's obviously going to be different for every app. It's definitely worth measuring. And I want to be clear that it's actually not the inflation time that's slow. We did an experiment where we did direct creation of the objects instead, and there's really not that much different. It's just these objects. The views are very large, right? A view, the base class for a view is 25,000 lines of code, and all the things that come with that, right? So even just constructing the classes still can take a long time. So we made that change. It was about half the time. It's actually quite tricky as well because there's actually a lot of really nasty locks inside the layout inflator. There's one that once you hit real scale, it can actually deadlock on specific devices. That was really fun to fix. So yeah, layout inflation, it's kind of tricky. But yeah, it's definitely worthwhile. It was about half of our latency when we first dropped it in.
Yes, on the back. The question was whether we're collecting performance metrics where we can see these improvements. The answer is yes. We have first we have performance tests that we run internally where periodically we'll just run an automated flow on a subset of devices and measure the performance. It allows us to catch regression, but also to compare it to versions of the app. And then we also run these same tests on production. The interesting thing about measuring performance in production is that your performance can get better or worse based on the population of users, right? So one thing that was very important to us is that we take the performance data we get, we break it down by things like device clusters or fix the same users, and then we compare those. Because otherwise, your performance could look much better. It could improve a lot between the months of October and December just because everyone traded up to a new device, but your app may actually have gotten slower.
Yes, the question is, given that we don't do preloading across screens, how do we make sure that the content loads quickly? And so, first of all, that was like the main thing we were testing in our initial kind of internal MVP of this is like, this is a good theory, but is it something we can actually do in practice? So most of the answers, like we did a lot of performance tracing along the way, right? Like we wrote the feature, we traced it and tested it to see how it was actually performing. So I think in this case, you're talking about doing an IPC to load the data from another source, which I think probably has a small hit. I think it would be worth measuring. I think probably the quickest win that you can get in trying to load your UI fast is to support some kind of pagination, right? Like our initial implementation of Friends Feed loaded, 200 items from the database, and that was a little bit slow, but really we only can see 10 on screen at a time. So once we just put a limit of 10, it's obviously quite a lot faster just to do that initial query. And then if you're using, recycler view and you're using stable IDs really correctly, then you can actually increase the limit of that query basically right away after your initial screen loads. So you have 10, and then you right away just load the 100, and you won't even see a flicker, right? Because the initial items will all map up perfectly. The IDs will match, so no change has to occur in the UI whatsoever. But that's why we actually invested quite a lot of time in this recycler view framework that made sure that once we made that change from paginated to full, the UI wouldn't change at all.
Yeah, I think to add to that, when we started working, it became very clear that one thing we had to do was move a lot of the processing that was happening at read time to happen at write time. Right? So when we first tried to load the friends incrementally, we ran into a problem where you want to go from most recent conversation to least recent conversation. But we didn't have a row in our database that said like last conversation timestamp. We had another table with the conversations that you had to kind of load and join into. It was very complex, right? So we had to really get into the mindset of the page has to be ready to go, and it has to be in a way that I can sort it and load it incrementally from the database. And once you have that, SQLite really helps you. You can hook up a observable to the data, and like Room also has pagination support. It becomes much easier to do, but your data has to be structured the right way. Question? The question is how much was testing considered as part of the effort? I think we consider a lot of things that are just good engineering practices, right? From modularization to testing to documentation to having fast builds and so forth. Yes, it was considered. We started monitoring code coverage, which is something that we didn't do before, so that we know like how we're training over time. We had labs where we would teach people to write tests. We wrote documentation on how could you do tests, and we have all these JUnit rules that will allow you to easily have versions of pieces of infrastructure to help with testing. So it was a big effort. I think another important thing was we didn't just do unit testing, we also did automation testing and performance automation testing, right? So that when something was working, it didn't always keep working. We had many bugs, but at least the chance that it kept working was much higher.
So we are out of time, but we're happy to stick around and answer any more questions you guys might have. Thank you.